In this video, we'll analyze the stability of a vehicle with respect to its yaw dynamics. Stability is a very important concept of any dynamical system and also, of course, for vehicles. In fact, the design of a vehicle would be considered rather poor if the vehicle is unstable. Remember that we're still talking about the open loop system, meaning the vehicle itself without the driver. As you know from basic control theory, it is generally possible to stabilize an open loop unstable system in closed loop. In this case, the driver, as the controller, would be the one to stabilize the unstable vehicle, and that's in fact possible. Nonetheless, for this we would have to rely on the skill of the driver. Therefore, it's considered undesirable and unsafe to have an open loop unstable vehicle. In the last videos on oversteer and understeer and the Understeer Gradient, we have analyzed the steady state behavior of the vehicle, where the vehicle was going on a stationary circle. Now we'll look at the transient response of the vehicle, in particular with respect to its stability. We will keep the linear bicycle model as the basis for our analysis, and that's for two main reasons. First of all, the linear bicycle model is a simple model. In particular, it's a linear model. This facilitates significantly our stability analysis because for linear systems, we have a very powerful set of tools and theory at our hands, whereas for nonlinear systems, stability analysis is a very complicated matter. Second of all, as we have seen, the linear bicycle model provides a very accurate representation of vehicle dynamics in the linear region of the tires. So at least up to the point where the tires saturate, our theoretical results will be very close to what's actually observed in reality. So let's repeat very briefly the results on the linear bicycle model that we have derived in a previous video on the dynamic bicycle model. So here's again a graphical illustration of the linear bicycle model, where the main parameters of the model are shown on the right-hand side. A main assumption was that the steering angle delta is small. The variables vlon and vlat are used to denote the longitudinal and lateral velocity of the reference point, where the reference point C is assumed to be also the vehicle's center of gravity. The variable omega is used to denote the yaw rate of the vehicle. As we have shown in all detail in the video on the dynamic bicycle model, this state space representation can be derived for the linear bicycle model. Note that here we have removed the third state, namely the yaw angle, as it is not important for our stability analysis. Observe that here we have the standard form of a linear state space representation, with the state vector consisting of the lateral velocity and the yaw rate. We have a system matrix A and an input matrix B, and the input is the steering angle delta. So we are in a position to use all of the tools that we have available for linear state space representations. And in particular, we can analyze the stability of the system by looking at the eigenvalues of the system matrix. As we know from basic linear systems theory, a linear state space model, in our case the linear bicycle model, is stable if and only if all of the eigenvalues of the system matrix are in the open left half of the complex plane. Moreover, the two eigenvalues of A, which we will call S1 and S2, satisfy its characteristic equation, which reads as the determinant of Si minus A equals to 0. Substituting the particular system matrix of the linear bicycle model A and the two-dimensional identity matrix I, we get this matrix whose determinant has to be 0. Using the standard formula for the determinant of a general 2x2 matrix, we obtain this expression for the characteristic equation of the system matrix. Clearly, this represents a second-order polynomial, and we can now go on with multiplying out these expressions in order to determine the coefficients of the second-order polynomial. So multiplying this out leads to this explicit polynomial, where we will call this coefficient b and this coefficient c. These expressions for the coefficients can now be further simplified by finding the least common denominator of these two fractions. We get this expression for b, and for c we move the term that we get from the multiplication of b ln with this expression first, and then we just add this term here and we subtract this term here. Then the first term is expanded with the factor m v ln squared, and this gives us the new first term. And the second term significantly simplifies by writing this as the common numerator and simplifying this expression to this expression up here. In the last step, we just write both terms which have a common denominator as one fraction, and we realize that LF plus LR equals to L, the wheelbase. Looking at the expressions for the two coefficients in a little more detail, we realize that the coefficient b always has to be positive, because all the quantities in this expression are positive and there's only plus signs. On the other hand, the coefficient c may be positive or negative depending on the values for the parameters. The roots of the second-order polynomial now follow with the quadratic formula stated here. As the coefficient b is always positive, which we have seen on the previous page, let's distinguish three cases. First, c is greater than 1/4 times b squared. This means that the expression under this square root is negative, and hence the two roots of the characteristic equation are given by a complex conjugate pair, whose real part equals to -1/2 b, and whose imaginary part w is defined as the square root of 4c minus b squared. Since the coefficient b is always positive, both eigenvalues have a negative real part, and therefore the system is always stable in this case 1. In case 2, we assume that c is actually less than or equal to 1/4 of b squared, but greater than 0. This implies that the expression under the square root in this case is less than b squared, but greater than or equal to 0. So in particular, because of this, the square root will yield a real value. More specifically, looking at the two solutions to the characteristic equation, they are given by this expression, where in this case the square root takes on real values between 0 and b. Hence, we conclude that in case 2, the eigenvalues S1 and S2 are both real and negative, so the system is stable. Case 3 is now the remaining case where the coefficient c is non-positive. This implies that the expression under the square root is greater than or equal to b squared. and hence the two roots of the characteristic equation are given by this expression, where now the square root is a real value that's greater than or equal to b. Hence, in case 3, the eigenvalues S1 and S2 are both real, with one of them being negative and the other one being non-negative. And because of that non-negative eigenvalue, we conclude that the system is unstable in this case. Given that case 3 was identified as the critical case, let's look at the condition of C being non-positive in a little more detail. And precisely this analysis will establish a connection between the stability of a vehicle and its properties in terms of understeer and oversteer. Let's start where we left off on the previous page. The necessary and sufficient condition for stability of the linear bicycle model is that the coefficient C must be positive. Now we substitute the explicit expression for the coefficient C that we have obtained earlier in this video, and what we get is that this term here has to be positive. Staring at this condition for a little bit, we can make the following observations. First, note that all quantities in this formula represent either linear or angular masses, lengths, or stiffness factors and are thus positive numbers. So no matter what parameter values we have for an actual vehicle, we see that if the longitudinal speed up here is small enough, then this first term here will be dominated by this positive second term, and hence the vehicle is stable because C is positive. Second, if the product of LR and C alpha R is greater than or equal to the product of LF and C alpha F, this means that in the expression for the coefficient C, this term here is non-negative. And so for any value of the longitudinal speed, we're adding a non-negative term to a positive term, which means that C is positive and hence the vehicle is stable. And that holds for all longitudinal velocities v lon. And third, if the product of LR and C alpha R is strictly less than the product of LF and C alpha F, this means that in the formula for the coefficient C, this term is negative, and hence by increasing the longitudinal speed, the first term becomes more and more negative, until at some point it outweighs the second term, which is positive. And so the entire coefficient C becomes non-positive, and hence the vehicle becomes unstable as soon as the longitudinal velocity increases above this critical threshold. So these are the three conclusions that we draw from the formula for the coefficient C, and now we compare these observations to the understeer gradient that was derived in the video on oversteer and understeer. Recall that this is the definition of the understeer gradient, and the vehicle is understeering if the understeer gradient is positive. It's called neutrally steering if k equals 0, and oversteering if k is negative. Recall also that WF and WR represent the weight factor for the front and the rear tire, so the fraction of the weight of the vehicle that rests on the front and the rear tire respectively. What we'll do next is substitute these simple formulas for WF and WR into the understeer gradient, and then we'll see that the gradient being positive, 0 or negative is closely related to the two stability cases that we have identified in our observations. And for convenience, we'll refer to this as case 1 and this one as case 2. So let's begin with rewriting the understeer gradient by substituting the expressions for WF and WR. Then by using the least common denominator for these two fractions, we get this equivalent expression for the understeer gradient. From the numerator of this expression, we see that there is a close relationship between the understeer gradient and the two stability cases that we have derived on the previous page. In particular, for case 1, where the product of LR and C alpha R was greater than or equal to the product of LF and C alpha F, is in fact equivalent to the understeer gradient being greater than or equal to 0. And correspondingly, case 2, where LR C alpha R is less than LF C alpha F, is equivalent to the understeer gradient being negative. So altogether, we may summarize our conclusion as follows. The first case, where the vehicle was stable for all longitudinal velocities, is equivalent to the understeer gradient being positive or 0, meaning that the vehicle is either understeering or neutrally steering. Hence, we can say that in order to be stable, a vehicle must be understeering or neutrally steering. Case 2, where the vehicle was stable up to a critical velocity, is found to be equivalent to the understeer gradient being negative, hence to an oversteering vehicle. So we can state that an oversteering vehicle is only stable up to a certain velocity, and it becomes unstable above that velocity. That's precisely the reason why in practice all mass market vehicles are designed to be understeering or neutrally steering, and an oversteering behavior of a vehicle is not deemed to be acceptable.